Yeah, okay. Sorry, or I will just go with this. All right, so let's get started. So my name is Jincheng Zhou. I'm a first-year master student at the University of Southern California. I've been working with Professor Paul Rosenblum and Dr. Wolfgang Wolfson for the past 3 years. So I'm very happy here to introduce you to our latest work, PySigma towards enhanced grand unification for the Sigma cognitive architecture. So I will structure my talks in 3 sections. The first, I will do a very short introduction to the Sigma cognitive architecture. Second one, I will introduce you to how we enhanced the Sigma cognitive architectures, which is a bunch of things that converge to a new version of it called PySigma. And third, in the final section, I will demonstrate the modeling of a deep generative model called variational autoencoder to illustrate the enhanced capability. All right, so what is the Sigma cognitive architecture? So it is a cog art that was proposed by Professor Paul Rosenblum and implemented back in 2009. It basically is a 2-layer architecture. So the first layer, the cognitive layer, or also called the cognitive architecture, specifies probabilistic logical languages that you can use to write cognitive models. The predicates are probabilistic that represent relational facts. The conditionals are also probabilistic rules that arrange these facts into kind of a graph for reasoning about these facts. And all of a cognitive model written in all of these languages will be compiled down to a graphical layer called graphical layer or graphical architecture into an augmented factor graph. So basically the predicates will be compiled to variable nodes, conditionals to factor nodes, and the inference is done by sum product message passing, and the learning is done by local gradient updates on the factor function in the factor node. One thing to note here is that this factor graph is augmented in many important ways, and the most important one is that it's lifted. So traditional factor nodes are only operates on single variables, but here the factors and variables are first order logics, probabilistic logics. So throughout the years of the research on Sigma, there has been 4 important design desiderata that has been in place to drive the research. The first one is grand unification, the idea that architecture should span both key cognitive and non-cognitive capabilities. One important aspect of that is to bridge symbolic, probabilistic, and neural processings. The second desiderata is generic cognition, which is the idea that this architecture should span methods and techniques from the research in both artificial intelligence as well as cognitive science. The third one is functional elegance, which is the idea that all of the above should be achieved via interactions among only a very small set of mechanisms, and therefore the overall architecture is functionally and theoretically elegant. And the final desideratum is sufficient efficiency, the idea that this whole architecture should be able to execute very quickly for any real-time applications. So throughout the years of research, there have been many achieved cognitive capabilities by Sigma. I'm not going to go into details of this. So if you are interested, please welcome to check out this paper by Professor Paul Rosenblum, published in the AGI journal back in 2016. So it's a 103 pages long paper detailing every design choices of Sigma and also the various cognitive capabilities achieved by Sigma. So although it has been successful to model a wide range of cognitive capabilities, there have been multiple major challenges. And 2 of them, as listed here, is inference learning with continuous variables and also a structured learning capabilities known as chunking. So the first problem, inference and learning with continuous variables. So imagine there's a let's say there's a predicate called location of O, X, and Y. Here, the variable O is a discrete symbolic variable that basically represents every object in the world. And XY here are continuous coordinates to model the location of these objects on a 2D plane. The problem with inference and learning with Sigma cognitive architecture is that the piecewise linear map, which is the fundamental building block for the message, tend to get fractured after multiple iterations of learning, which I will illustrate later. And the second thing called structural linear chunking, this was implemented in the SOAR cognitive architecture, which is a predecessor to Sigma. What it does is basically it summarizes a bunch of complicated symbolic rules into one single efficient rule. However, due to the probabilistic nature of Sigma, this has not yet been implemented because essentially it's hard to summarize probabilistic rules. So now I'm going to move into the second part, which I introduced PySigma and how we address this problem. So it basically started off as an attempt to address this first challenge. So here's an illustration of how the piecewise linear map is getting fractured. Basically, after multiple iterations of learning, it will become spicy and sorry, not spicy, spiky. So unless proper smoothing is introduced, what you learn is basically nonsense. So the approach of PySigma has been to completely rethinking the graphical layer of this architecture. What we're doing here is to overhaul the entire graphical architecture in three major ways. One is to design a completely new message representation, accompanied with a generalized message parsing algorithms, enabling approximate inference on the continuous variables. And also the whole thing is built upon PyTorch so that we can leverage PyTorch's computational graph for efficient gradient-based learning. Although we overhaul this entire underlying graphical architecture, we also keep the same design principles for the cognitive architecture, which is the first layer. And therefore, the cognitive language provided by the first layer is very similar to Sigma. And in principle, every cognitive models you write in Sigma can be ported to PySigma as well. So you may ask why we want to overhaul the graphical architectures, why not just introduce smoothing? Well, again, the idea goes back to the 4 desiderata. We want to have a functionally elegant grand unification. And it has been attempted before that introducing smoothing techniques was very non-elegant and adds a lot of very subtle difficulties. All right, so now I'm going to go into the technical details of PySigma. So the first thing is about the message representation. So again, message representation in Sigma was done via piecewise linear functions. Again, as you can see here. However, in PySigma, we are doing it completely differently. So we first distinguish the difference between relational and random variables. We make the assumption that so basically, we view relational variables as the symbolic and discrete things that describe discrete concepts or objects in the world. Whereas the random variables, it may be discrete or it may be continuous, but the assumption here is that they are sampled jointly from certain distributions. And therefore, here we have the explicit distributional assumptions. You can think of each predicate grounded by the relational variables here. For example, if you go back to the locational predicates, if it's grounded by the relational object variable, it's basically a batch of independent distributions. There are two ways we approach the the representation of this distributional assumption. The first way is using parameters. Basically, in this type of message, we assume that the distributions can be parameterized. For example, natural distributions or Bernoulli distributions. So here is an illustration of that. You will have a predicate which has basically a batch of 3 parameterized distributions. So again, the relational variables here will be the one that organize and index a batch of distributional instances. The other way is we use the particles type of messages. So this is different from the parameter representation in that we do not explicitly assume that the distribution can be parameterized. Instead, we are using particle list to approximate the distributions. So there are 3 important parts in this data structure. First, we have a particle value. It's basically a vector, are storing the value assignment to the random variables. We also accompanying this, we have a weight vector, which is value in 0 and 1 associated with each particle. But the most important thing is the third one. It's a sampling probability. So it's the probability density for the particles that are the probability density of them from the originally sampling distribution. So why do we need this here? The idea is that with all these three components, we are able to perform an important technique called importance sampling. So the idea is that when two messages are summed up in the factor graph, basically what it's doing under the hood is importance sampling. So one message may borrow the particles from another messages and reweight its weight vector. So that was the first important change. And the second important change is that we generalize the notion of the factor function in the factor nodes. Now, in the sigma, it was represented via piecewise linear map again. But here now, we generalize it and we distinguish it between a generative and discriminative factor functions. Anything that kind of fall into this mathematical formulation can be considered as a valid factor function. The reason for doing that is now this allows function approximators such as neural networks being used as the factor functions. So the third thing which is very important and one of our major contribution here is to propose a generalized message parsing algorithm. There are lots of technical details, so I'm not going to go deep into them. If you are interested, please check out our paper. But basically, there are two modes of this generalized message algorithm. The first way of doing it is so-called the variational message parsing. The idea is that in the most simple mode, the message being passed are the natural parameters for exponentially family distributions. And if the messages are from exponentially family and the factor functions are exponentially conjugate, then there's a closed form solution for the message update rules. If not, we fall back to stochastic updates where we use Monte Carlo method to approximate the posterior. One thing to know here is that at a variable node, if we use the stochastic version, it actually mathematically lends itself to the math formula that's equivalent to an algorithm called proximal policy optimization, which is a very well-known algorithm in reinforcement learning. The second mode is the Monte Carlo message passing that's being adapted from the particle belief propagation algorithm. Basically, it's just passing, instead of passing parameters, here we are passing Monte Carlo particle list, and it achieves the same result. And how it does the inference is basically at the variable nodes using algorithms such as MCMC to approximate the posterior particle list. And the final thing is that this whole thing is built onto upon PyTorch, and therefore learning can be done in the PyTorch computational graph. And what the architecture does here is to carefully control the scope of the gradient flow so that independent parts of the graph doesn't interfere with each other. Right, so the final part of my presentation here, I'm going to demonstrate the modeling, this kind of enhanced capability by demonstrating how to model a deep generative model known as variational autoencoder. So first thing why we choose that is because variational autoencoder is a very simple latent variable model. It's just having a sorry, that should be, the z should be gray, but having an observed variable x and then latent variable z. On the other hand, however, it's a perfect illustration of the synergy between probabilistic processing and neural processing. So it's a very good way to show how different, symbolic, neural, and probabilistic processing can be combined together. So in the VAE, there are two important tasks. The first is the inference task, which is that given the model, conditional model, infer a posterior of the latent variable. And the second one is that fix the data. We want to select a conditional model that best fit the data distributions. So if you want to, VAE has this loss function called evidence lower bound, or the elbow objective. By optimizing on these loss functions, you simultaneously solve the two tasks at once. So if you want to model VAE as a as a PySigma model, we first need to convert it into a factor graph, right? So here's a naive attempt at doing that. Basically, we just have a prior factor node and a conditional factor node. However, the challenge here is that this is not that easy to solve, because if you see there in the elbow equation, the final term, which is also called the recognition model, it's negative, and it's not very simple to model negative term in using naively propagation algorithms such as sum product algorithms, right? Because everything in the sum product algorithms are getting summed up, not being subtracted. So how we resolve this issue is that we know that, again, in the particles representation of the message, we have this term, the sampling probability. And therefore, we can introduce an additional pathway here, which is directed, that lends itself to the augmented factor graph. And this node is basically, you can treat it as a sampling factor node, where you are sampling particles from this distribution with uniform rates, but not uniform sampling probability, which is exactly, this term here, the probability density. And there's a lot of technical details. You can check our paper. But the conclusion here is that because of doing that, when the message are getting summed up here at the latent variable nodes, due to importance sampling, we have this term here, and that effectively turns the Q of Z of given X into the denominator. And if you transform that into the logarithmic space, it is the negation term. Therefore, so here is an excerpt from our paper, which is a detailed breakdown of all the messages passing around. And we show mathematically that if we do it this way, the overall model will reflect the elbow objective. So here is how the model will look like in PySigma. There's a few special cognitive nodes that's being used here for the modeling of VAE. So first thing is a working memory factor node. And in this case, it exactly was the sampling node that we just shown. And the perceptual buffer factor node, PBFN, here is responsible for perceiving the observation data. And the optimization factor node here is to compare the observed data from the messages that's coming out of X to calculate the loss function that maximizes the data likelihood. Another thing to note here is that now the factors P of X given Z and the Q of Z given X, they are factor nodes with neural networks as factor function approximators. And therefore, this basically just implements the VAE in its neural network form with probabilistic models in PySigma. All right, so the conclusion, what is PySigma? Why is it important? So first thing first, it's an enhanced Sigma cognitive architectures. It fundamentally redesigned the graphical layer to enable continuous approximate inference and learning, and therefore make it able to model a wider range of capabilities. However, it also inherits all of the cognitive capabilities because it follows the same design principle for the cognitive layer. You can also think that by itself, it's kind of like a generalized inference engine on graphical models with, of course, the augmented factor graph as the underlying representation. And basically, the mission of PySigma is to move towards grand unification. So, yes. So let me just briefly talk about the future work that we are going to do. This is still an ongoing project. So one thing is that we'll attempt to resolve trunking with these enhanced capabilities. And why that may work, because we just make one important observation here is that, again, in this VAE formulation, we recognize that we observe that these sampling nodes may be applied to arbitrary graphical pathways to approximate the posterior distribution of any given predicates. And in that case, it's basically just using variational inference plus neural networks to approximate the complicated probabilistic, symbolic, and relational processings. You can think of that as kind of basically building a system one processing pathways to approximate the message calculation via a system two pathway. And the other thing we can do, we will want to do here is knowledge graph identification and also causal reasoning. So here, allow me to borrow a screenshot from today's morning's presentation by Yoshua Benjo. So actually, I was surprised this was added this new, but I think he's doing actually some very interesting work on causal reasoning over factor graph. So I'm really interested to see what comes out of all of that. All right. So just on the last note, I want to say a huge thank you to Professor Paul Rosenblum for his comments and continuous support throughout the past 3 years. Without his support, this work wouldn't have been made possible. So again, thank you very much. All right. So thank you.
You're close. Thanks so much for that, Jiancheng. And finally, Samuel, to wrap up the day. Thank you.
Hi, I feel so welcome. I'm so good. Milk cow.
Fantastic, thank you. So specifically, I'd love to get a question for Tyler, Jiancheng, or for Christian. We haven't had any questions on this side. Anyone got anything to ask? This is Ben coming up.
Yeah, this again isn't quite a question, but might lead to a question. But I thought it a conversation Jiancheng and I were having in the hallway before seemed like it could provide some interesting context here. And what we were musing about was, you know, if factor graphs are not an adequate representation for everything a general intelligence needs to do, but we're a good representation for some of the things that general intelligence needs to do, how would you work them into some sort of more general framework? And I mean, there could be a lot of ways to do that. So I mean, Yoshua Bengio in his talk today was suggesting you could, in essence, expand factor graphs via lifting in various mechanisms to make them more general, which is one direction. Another direction, if you have a framework like the meta language that Alexei presented on Friday and Jonathan Worrell was sort of formalizing in this talk, this is a language in which the whole purpose is to create various DSLs, various smaller languages within the meta language. One could then, in effect, create a factor graph DSL within the meta language, and then something like some product algorithm would basically be wrapped up within a specialized type checker and type inference mechanism for that factor graph DSL. And where you would really be getting in the full-on AGI direction, though, is when some learning mechanism figured out that creating a factor graph DSL is a good thing to do. But at the current stage that we're at, what you could do is like create a DSL for factor graphs in the meta language, which is more general framework. Then when something matches that, you do that, but then you can sort of go back and forth between the factor graph learning and other sorts of reasoning and learning within the whole meta framework. So I think there's what Jiancheng presented is quite interesting, and I'd say Yoshua gave one way to extend that sort of thing. I gave another way to extend that sort of thing, and maybe that. I guess if I have a question, it's do you and Paul have some other idea of how to sort of extend this to give it more general representational capability?
Right. So I think Professor Paul actually have a talk tomorrow, so I'm welcoming everybody to listen to his talk. I think maybe this is one question you can propose. But from my understanding, yes, in terms of so one of the 4 design desiderata for the Sigma project has been the functional elegance, right? The idea that architecture can be very complex. It can model a wide range of capabilities, but it should stem from a very functionally and theoretically elegant base. And so I'm not sure whether factor graph can be universal, functional, universal base for general intelligence. Currently, I'm just being exposed to this meta language and meta graph, so I need a lot of mathematics, lectures to catch up. But let's say, suppose meta graph has this capability to kind of instantiate the factor graph, then I would think it will be an excellent candidate for being the functionally elegant base, right? Such a representation, because as far as I know it, let's say the knowledge and skills, right? The knowledge can be represented as metagraph, and the skills are basically transformation on the metagraph, which is a variety of all kinds of fancy word for morphisms. And this morphisms can also be expressed as metagraph. So in this case, I think there's nothing different in terms of data and processing. They are just graphs. And so if this is the case, I would say it's a very functionally elegant representation. And I would think perhaps Professor Paul Rosenblum would also be in favor of such a representation, because again, it falls back to the desiderata, and it's very good in this sense.
I would say, elegance is a constraint that you might want to throw out the window, and, put together some kind of kludge where you incorporate the best parts of all, the systems that you find interesting. So include.
We did that in 1998. It was called WebMind systems. In the following decades, we found that getting shit to work is easier and easier if you manage to factor out the common elements of your design to a small set of mechanisms. It's just easier to engineer for efficiency and easier to tune the system that way.
Right.
Even if theoretically the kludge could have the same kind of functionality.
So even if it was done once, that doesn't mean that you use the same requirements this time around. So you may have different requirements now than you did before. And the only other thing I would say is that, like NARS has very elegant ideas. For example, the confidence and the frequency, that's very important. Factor graphs as well. So you can put these elements together, and I think that would be helpful.
This is like future to the past, right? So in 1998, when I tried my first hybrid AI project and hired Pei Wang, the creator of NARS, as our director of research, we did actually kludge together NARS with genetic programming, with attractor neural networks, and various other things in the same distributed hypergraph-based system. And it is also true the brain is kind of a kludge, right? I mean, but it's a kludge that took a really long time to evolve, with a lot of trial and error and a lot of dead suffering systems along the way. So I mean, as I've progressed in the lineage of hybrid algorithm AGI systems I've tried to build since then, I've been moving further and further away from the kludge approach. So the big difference between WebMind and Novometic Cognition Engine, which became the original version of OpenCog, is that we were being very careful to make sure all the different AI algorithms acting together on the atom space had a common semantic understanding, right? And now the work that I've been doing the last year or so is aimed at making all the AI algorithms acting on that atom space, enact the same basic dynamical template that can be boiled down to the same small set of functional programming operations on the metagraph. So I think you could build a lot of AGI systems. You could build kludgy ones or elegant ones. My hypothesis is, if you're engineering and not evolving, the kludgy ones are going to be incredibly hard to get to work right and to debug and just maintain.
Unless you have requirements. If you have good requirements, then that might be.
Oh, let me let Linus give his own view on this, actually.
Yeah, this was, again, more of a comment rather than a question, but I wanted to point out factorization also provides a way of generalizing, and generalizing we heard throughout the talks seems to be a difficult thing to do. Now, the way factorization generalizes, a lot of complex problems cannot be exactly factored unless you ignore certain small details. And if you ignore those small details, then you can split them into factors. In ignoring those small details, you've sort of generalized and said, oh, well, okay, those details didn't matter. So by factorizing, you have a way of generalizing from specifics to generalities. And that's the strength of factorization. I'll pass on the mic.
Okay, and then I'll return it. So one of my favorite knowledge representation people is Richard Mikowski, and Richard Mikowski he put together some very good definitions of terms. One is generalization versus specialization, and another is abstraction versus concretion. And so in Richard Mikowski's definition, abstraction is when you eliminate information. So suppose you have a set of items and you remove one item from your set, then you're abstracting. When you have a set of items and you introduce more items into the set, then you're concreting. And then generalization and specialization is actually having a taxonomy or a ontology and moving elements up or down in the taxonomy. So he, I liked his approach to defining these terms.
Factorization combines those. All I have to add is factorization combines all of those into one step, as it were.
That could be problematic or not.
Well, it's not a solution to everything. Any remaining questions? Oh.
Yes, so just to add kind of like a comment, following all of this discussion. So yeah, I'm in support of, I do feel like this desiderata for Sigma of this thing called functional elegance. It's less of a strict requirement that it's being applied to the architecture, but more like a kind of an expectation or kind of a regularization on the actual research process that we did here do in Sigma. So actually throughout the years of research at Sigma, there has been various attempts at, introducing new capabilities at the expense of sacrificing functional elegance. One example is the augmented factor graph. So originally it wasn't proposed to use this factor graph, and I think the general conclusion was that we should be very hesitant to, let's say, introduce unidirectionality in the factor graph link. But it turns out that without unidirectionality, many processing you just cannot model. For example, neural networks or symbolic rules, they are unidirectional, right? So I think, and this has been done, but later the general agreement is that although it's necessary to make compromises, in which way can we make such compromises in the minimalist way? And I think this has been the general philosophy that guides the Sigma research. And I think many of things are, because we don't have AGI yet, so we don't know whether it's a good principle or not, but from our experience, it has been very valuable.
Yeah, I mean, balancing mathematical elegance with sort of the practical compromises you need to make to get stuff working with limited resources on the particular class of problems you care about. I mean, this is going to be an ongoing fudgy balancing act, right? And I mean, the human brain has general purpose mechanisms and then a lot of dodgy special purpose adaptations. And I mean, quite possibly any practical AGI system that's sort of biased to be a human-like general intelligence is going to have its own kludginess about it in some way or another. So I think that's like dancing between beauty and practicality, something everyone's going to have to do in crafting their own AGI system. And the compromises often look weird from the outside, but you see clearly why you made them when you're working on the system.
Well, I mean, I think the evolutionary neuroscientists can be even a little bit more accurate. They say some of the simplest parts of the brain that are highly conserved, right, solved a certain set of problems. After solving those problems, the organism, in a certain sense, the evolution stops there, but the next level up is to build a control mechanism on top that resolves the more difficult problems, that partly resolves those more difficult problems, but then you run into ever higher increasing hierarchies of problems, but you still needed to solve the simple ones, which is why those brain regions are conserved across families, basically.
So I think That's all true.
In the case of jellyfish, I think the canonical example in case of a jellyfish is a jellyfish can either, it can tries to eat while it's running away because its neural system, its neural network is trying to solve both problems. And it needed a higher control mechanism to basically shut down the urge to eat while it's fleeing of its predators. And to shut down the flee mechanism
I can eat
while it's, when there's no...
I'm a higher form of life. Yeah, maybe. Yeah. But on that note, it's about time to go eat, hopefully without fleeing any predators. And we're also going to get kicked out of this conference room soon. So yeah, let me thank our afternoon session presenters for some really cool talks and Q&A. So thanks everyone. And yeah, thanks to the online audience with your patience and persistence with a problematic IT system here in Palo Alto. But hopefully the really interesting concepts got through, and we're going to begin again, I believe, quite early tomorrow morning Pacific time, which may be even too early for the face-to-face people, but we missed David Hansen's keynote this morning. David's on Hong Kong time. David, I believe, is going to try to deliver his keynote at 7:30 a.m. Pacific time, and so for online participants in different time zones, this should be quite convenient. For face-to-face people, show up at 7:30 or watch David's keynote on YouTube afterwards, which I'm sure will be a great one. And then after that, 8 a.m. tomorrow, we have more contributed talks, and we're keep on rolling for one more day of the AGI conference. We've got Gary Marcus tomorrow. We have Yosef Urban explaining the path to superhuman theorem proving, and lots of amazing stuff. So everyone, please come back tomorrow for the final and perhaps greatest day